So I would like to introduce Professor Andreas BIRK from the University of Bremen, and most of you who know BtS know him well already. He is going to be talking about underwater human-robot interaction, an overview of the history, challenges, and methods.
So, welcome to my presentation. It's largely based on a related work discussion in a recent robotics and automation magazine article. So I just do a little bit of shameless promotion for that article here right in the beginning. I'm also gonna have quite a lot of references in my presentation. So I'm also gonna provide in the end a URL with a link to the PDF so that you can have a look at the references. So the talk is structured fairly straightforward. I'm just going to give a very, very short introduction with a motivation. I'm going to talk about robot-to-human interaction and human-to-robot interaction. I'm going to dive a little bit deeper into the issue of gestures, and then I present a few conclusions. So for the introduction, first, I mean, the motivation is relatively straightforward and simple. Human divers are still very important in practice. This holds especially for fast and efficient interventions. So marine science, meaning sampling, archeology, also oil and gas production, handling of unexploded ordnance, so UXO, or maintenance of marine infrastructure, harbors, renewable energy installations, and so on. But the state of the art, especially when we look at applications, is actually that we more have like a coexistence of divers and robots. I love this video from Oceaneering that they have put on YouTube. You know, they call it Robot Diver Corporation, but actually the diver is just using this ROV as a kind of platform to crawl around, to access some stuff, and the level of real collaboration is actually very small. So the core basis for robot-diver interaction or human-robot interaction underwater is actually diver detection and tracking. This is a very well-established research areas. I do have a bunch of references here. As mentioned, I'm going to provide the PDF so that you can have a look. Most probably here now on that screen, they are too small to read them. But you can see that, you know, starting from 2007, there might be even earlier references, but I didn't find them. Starting from 2007, you do have quite many publications on it, and you will see that there are all kind of different sensor modalities used, typically vision for the near field, both monocular and stereo, but also full range of acoustic, both active and passive, so pingers, sonars, and detecting the sound of briefing apparatuses are examples. You will also see that you find the full range of the standard computer vision plus artificial intelligence and machine learning methods. So actually, for diver detection and tracking, you see in the literature the full standard repertoire of underwater object recognition and localization. So the methods and the sensors used typically, you know, could be used for all kind of different objects that you want to recognize and localize. Now, I'm gonna talk in my presentation here a little bit more about what I would consider to be proper human-robot interaction, which involves communication. So collaboration or real collaboration requires the exchange of information. So we need to exchange information about states, of the actors, the current mission execution, and so on. Intentions, if there's, for example, a dynamical mission execution, and also feedback in the case of failures. So we need to communicate, and this is obviously a bidirectional thing. So we have the aspects of robot to human communication and of human to robot communication. I'll start with the robot to human. The simplest form of communication, of feedback from an underwater robot to a human is actually lights. So the video I have here is actually from the Caddy project, where we have already heard a little bit about before. So with blinking lights, I can very easily give some feedback, you know, that a certain gesture or command was at least understood, you know, or that something was recognized or detected, not necessarily the right kind of command, but, you know, to have at least a certain kind of feedback. It's very simple because typically lights are already on any AOV or ROV, but it interferes with vision. So when you're, you know, changing the states of your lights, obviously you change the illumination. Plus, you have a very, very low expressive power. Interesting detail is the only early publication I could find where blinking lights are explicitly mentioned is actually a paper from the group of Howard on underwater human-robot communication, a case study from 2014. I'm very well aware that blinking lights have been used for feedback already earlier, including own work from 2011, but we just didn't mention it in our publications because it was so obvious. If anybody is aware of earlier publications that explicitly mention blinking lights, I'm very glad, happy to get that information. So another option is robot motion, which is actually conceptually relatively interesting. So there is a paper by Fulton et al. Using their Aqua robot to actually perform chimemes, which is a concept from semiotics. So actually communication or the science of symbols in general, and or the science of meaning, and it's a concept from nonverbal communication. So the idea is that the robot does certain form of motions, which to some extent are also very intuitive to humans. So when you pitch, you know, the head of the robot or the front of the robot, this signals a yes. If you know, shake the front, so you yaw, this is a no, and so on, and so on. So it's conceptually relatively interesting. The problem is that your robot has to have certain capabilities. I mean, there are many platforms, larger ROVs, larger AUVs, where you can't just very easily pitch the robot. Or this robot they used, it has flippers, so you can use the flippers to actually, you know, wave and signal. I mean, most robots don't really have this kind of actuation, so you cannot use it for the communication. I mean, I kind of really like it conceptually, but to use it in practice, I think, is difficult, especially as you still have relatively strong limitation on the expressive power. And then there are displays. Displays are actually quite interesting. One of the very early work on it is actually Aqua Tablet, which has been developed in the group of Jenkins. There you have just underwater tablet, which means a waterproofed tablet, which is carried in that work by the diver, and you have a tether from the tablet to the robot. So this TEVR has a very high bandwidth because it's an optical fiber. It has a low latency, and the big advantage is that you can use a detailed GUI so that the diver gets really a lot of information from the robot. There is also the option to use it not only robot to human, but also human to robot. Though in that paper, they only speculate about that option. So they're saying like, okay, we might use the IMU to have, you know, a Wii controller-like feedback, or to use it as a kind of joystick, but it was not really used. But it's important that this is, so to say, early work on an underwater tablet from 2010. Then we do have the Caddy Tablet, which is on the robot itself, can also be used by the diver. It's actually proper bidirectional. It's with input through a waterproof inductive pen. And it's actually work by Nicholas' group. Unfortunately, there is no paper, no reference on just the tablet. So I do have here a reference that is actually from the Caddy project, and all different partners involved in that project. But the credit for that tablet should actually go fully to Nicola and his group. But like I said, the only way to actually cite it, to reference it, is this publication. So displays do have a little bit of disadvantages. So you obviously need a dedicated hardware, but I think the amount of need for this dedicated hardware nowadays is small. I mean, you can even use something like an Arduino or a Raspberry Pi. You have very cheap, very good displays for them. To put this into a waterproof housing, I think is not that challenging. And the nice thing is, it doesn't interfere with other tasks. So if you move your robot to give feedback, you obviously interfere with perception. You know, if you're pitching the robot, you can't at the same time look at the diver. If you're flashing lights, like I said, illumination changes can also mess up the perception of the diver. So it's a dedicated thing, which I think is a plus. The hardware is not necessarily that expensive. And you can have a very high expressive power, especially text, color, blinking. If you want, you might even have a GUI, but typically GUIs, my personal opinion is they are overkill. But personally, I would say robot to human, this is kind of a preferred option. Now let's have a look at human to robot. There is very early, first I'm also going to shortly talk about tablets. So we can obviously also use the tablets not only robot to human, so if we don't just use a passive display, but something more advanced. But if we do have something like an inductive pen or any other forms, then we at least need some close proximity, respectively even physical interaction with the robot if you want human to robot input for underwater HRI. Or you need the diver to carry the tablet and then need to link it via tether or acoustic link. So, I mean, it is an option, but I think there are certain limitations. Now, very early work on human to robot communication underwater includes, or is this paper by Dudek et al. On using fiducial markers. The idea is actually very simple, especially 2007. The possibilities for fast and very robust underwater perception were still limited. I mean, partially it's also a matter of hardware. What kind of computer power do you have underwater? What kind of, methods can you actually efficiently implement so that you get a fast recognition rate? And their idea was to use fiducial markers, concretely AR tags that are carried by the diver and presented to the robot. So their paper deals mainly with using different forms of collections that you see there on the right-hand side. So they actually collected them in terms of booklets, cubes, decaeders, and then the diver is supposed to show them to the robot. The robot recognizes the tags, which works relatively well underwater, and then, so to say, interprets them. I'm going to say a few words about how this interpretation works later on. One slight disadvantage of that work is that the main evaluation is in air on land. So the deal is that they achieve a very robust classification using these fiducial markers. But with these fiducial markers, you do have quite a limited expressiveness. And I think the main difficulty is the handling for the diver. So imagine as a diver, you do have a decaeder that you have to, move around and show to the robot, and you have to have this thing, somewhere stored ready. They compared it to gesture interpretation in a Wizard of Oz experiment. So there was a human interpreter that looked at the gestures, and they found a relatively obvious thing that, the gestures actually would be preferred, so normal hand gestures over the AR tag markers. But the main problem is, of course, these gestures are much harder to perceive. As already mentioned, we also have to keep in mind this is 2007, where underwater vision, both from a methodological viewpoint and especially the typical kind of computer hardware that you had available, was still very, very challenging. So gestures are something relatively natural, something quite preferable for human to robot communication. So I'm gonna dive a little bit deeper into that topic. Early work, and if I'm not completely mistaken, even first work to underwater human-robot interaction with gestures is actually own work from 2011. There we had the idea to use a spectral registration to do image stabilization of video frames, and then it's very easy to do differential imaging. So based on the differential imaging with very classic computer vision, we could very easily get motion segments, and we just used finite state machines for classification and interpretation. So we used both arm motion as well as hand motion. To be honest, the waving arms underwater are not such a great idea. So when you're underwater and you start waving with your arms, what a surprise, you might start moving. The good thing is, due to this very robust registration, we nevertheless got very good differential images. But the hand gestures actually worked very well. So things like stay at same depth were very robustly detected. So it's very simple, very robust, but the big disadvantage is you only have dynamic gestures, and because you can only detect the dynamic gestures, you do have limited expressiveness. Nonetheless, it's definitely work on using hand gestures underwater already 2011. So in general, I think it makes a lot of sense when it comes to gestures to actually distinguish between the gesture front end and the gesture back end. That's actually also introduced in this Robotics and Automation magazine article that I have just mentioned in the beginning, which is very recent. So it just came out a few days ago. So the idea is actually that we do have a front end in the sense of we need to perceive the gesture in the sense that we need to have a mapping from sensor input to actual symbols. So we need segmentation, detection, classification. And then we have the back end where we actually have the symbol interpretation, where we map the symbols to commands, parameters, and so on, where we can use a grammar to increase the expressive power, and where we also need to handle errors and feedback, because it's an illusion that, you know, we just could signal stuff and there would never ever be a misinterpretation or wrong perception or just no perception at all. And the main deal why it makes sense to separate these two different aspects is because we obviously can use very different back ends with very different front ends. So if there's a good solution for a front end, there might be different back ends and vice versa to combine with. So let's start with having a short look at back ends. The paper that I've already mentioned by Dudek et al. From 2007, so very early work on underwater human-robot interaction. There we had the fiducials, so these AR tags for the front end. And for the back end, they actually proposed a kind of programming language. So on the right-hand side, you see this context-free grammar in Bacchus-Naur form or BNF form, where you, so to say, can program the mission in situ underwater. So you have actions, parameters, and so on. You have a conditional, so an if. You can even have function blocks. So I think it's an important idea already from 2007 to say, like, okay, we need to, so to say, structure the interpretation of these gestures, but it stayed on a rather conceptual level. So in their paper, they really describe it like there is an instantaneous perfect recognition of commands. So you just program this by showing it to the robot, and then you have to execute a tag, and then things run. So there is absolutely no handling of failed or false gesture recognition. Nonetheless, like I already said, it's very early work, which definitely has to be acknowledged, and there are very good reasons why they used fiducials to handle this challenge of the front end. Then for the gesture back end, I think we also have some very, very nice solution in form of Caddy, which is derived from the routine communications of divers. There is a phrase parser, syntax checker, command dispatcher, so there is a full system to actually, so to say, take care of the back end. For the front end, multiple options were tested. I'm going to talk a little bit about this. So you see here on the, oops, sorry, I'm getting old. So you see here on the right-hand side the structure, and you also see that displays are used for providing feedback. This A and the A upside down are actually delimiters that are used to, so to say, structure the commands. So you do have this mapping of gestures to symbols. You do have a start of a command. Then you can also provide parameters. For example, for go down 2 meters, you need to provide the parameter 2 meters. So you have the start of the command. You do have the command proper, so to say. Then the parameter here 2 meters. And then you have the end of the command. You can even specify complex missions. And on the right-hand side, you do see the context-free grammar in Bacchus-Nauer form again. So the deal is that also things are grouped into different large groups. There are 6 groups of commands and messages. Also, there are things like the diver can signal that he or she has certain problems, which then can be used by the robot to take appropriate actions. So, for the sake of time, I won't go too much into detail. As mentioned, I'm going to provide the PDF with all the references, but I am so bold to say that, if you have a deeper look into Caddy, it's actually for the back end a prototypical solution. Okay, there can be very good reasons to extend it or modify it in some respects depending on the application. For example, if you deal with underwater unexploded ordnance, you obviously need to have some according symbols and syntax for it, and you might have an additional group of commands. But in principle, the basic concepts are there, especially with respect to how to form complex commands, including parameters, and how to form mission specifications. So one big advantage is also that it's very intuitive for divers because it's strongly related to the gestures that divers are already using. It has a very high expressiveness if you need it, but at the same time also there are so-called slang commands where you don't have to have this start command, provide command proper, where you just show a single gesture and it's immediately interpreted, something like take a photo, you just say take a photo and you don't need to specify take this photo, start, and so on. And as mentioned, it's a fully integrated system. Now, let's have a look at front ends. So the deal is for the front end, we need a mapping from sensor data to the symbols. And we can, for example, also use different sensor modalities, like, for example, an imaging sensor. There is work from Nicolas' group actually on that, which is very nice. So an imaging sonar is combined with classic computer vision and machine learning methods. So an important detail also in that work is that we need to take care or need to have in the back of our mind that there's also the issue of hand segmentation and then the gesture recognition. Recently, a bunch of papers are popping up on underwater gesture detection, and I'm going to say a few words about that in a second, that use deep learning and whatsoever, and where you have the hand just in front of the camera and nothing else. You don't even see the diver, So it's okay-ish, but please don't sell it as a complete working solution, and we are the first ones too. The deal is, when we're talking about reality and in practice, for the front end, the hand detection segmentation can be, respectively, is a challenging part. So I won't go into the technical details. Like I said, you have the publication references, you can look into it, but it's very nice work on using imaging sonar to do gesture recognition. It has the usual disadvantages of imaging sonars. So it works in very low visibility conditions, but each of you who has worked with an imaging sonar, the parameter selection is a pain in the meep. So, period. So, to be honest, I haven't seen any work yet that manages to have a, so to say, auto selection of parameters for imaging sonar that is really convincing, but maybe this might be popping up in the future someday. So, as we have seen also just before this talk, there is also an interesting direction of using smart diving cloths, which might be a good alternative to ease perception, because you actually don't really need the classical underwater sensors perception anymore. I think it has a lot of potential. You need a bit of dedicated hardware, but I think that's just a very minor issue. From all I know, the cheap capacitive strain sensors used to have quite some wear issues in the past. I hope that's gone. One part of me hopes that's gone because then there is a solution. The other part hopes it's not gone because then I still have some research. No, I'm just kidding. So this might be a very promising thing. But most of the work we see today is actually using just classical vision for the front end parts. So in Caddy, we used actually colored gloves that you can here nicely see on the image. So the diver gloves have some special visual markers. Professional divers wear gloves anyway, so this is not that much of an issue. Also stereo camera, and in general for underwater vision, I can only recommend stereo. With depth information, image restoration gets much easier, segmentation gets much easier. I mean, it's still hard, but it really helps a lot. So in the early work, we actually used very classic computer vision and machine learning, which actually gives a very good baseline performance. We have a special form of decision tree machine learning. Again, no need to go into the technical details. And the interesting detail is it gives a good baseline performance, but far from optimal. So what does that mean? In this recent robotics and automation magazine article, we actually tested multiple forms of deep learning and this very classic machine vision, machine learning based perception for the front end. And the deal is, not so surprisingly, I mean, sometimes the deep learning performs incredibly strong, or certain forms of deep learning approaches perform incredibly strong, while others perform incredibly poor, and it strongly depends on the training and the testing data. I mean, the deal is, underwater we have an incredible amount of variation of visual conditions due to the environment factors in the image formation. This is a very trivial insight, but tremendously important. I currently see a lot of papers popping up using deep learning on underwater X. So don't get me wrong, deep learning can make sense. It can be very, very powerful. But these type of papers, we have one data set recorded in one location under one specific type of condition. We train on half of it, and then we evaluate on half of it. We change half a parameter, and we get an epsilon improvement. Yeah, and we have a paper. I mean, it's nice from the perspective of you have an infinite paper production machine, but using this stuff then in reality, hopefully nobody does if it's, for anything meaningful. So the amount of variation of environment factors, especially underwater, is a very critical issue. So it's a little bit hard to say, what of these various methods we've tried is actually good or bad. There's a clear it depends. And there's also quite some other work. I just cite a few ones which are actually relatively high quality. Like I said, there are also a few very recently popping up which are, like I said, just the hand. You don't see a diver recorded under single conditions, and just applying deep learning. So the deal is that, like I said, deep learning, it's a trivial insight, but it's important. It depends a lot on the training data. So for the gesture recognition, there is, by the way, a large data set available that has been generated in the Caddy project. So here is the publication that points to it. And more importantly, we also use in this robotics and automation article artificially degraded data. And I think that's another deal with the depth information from the stereo, that when you have depth information of your scene, so when you have range information, you can generate physically very plausible degradations. And with that, you can simulate a huge range of different visibility conditions and simulate a huge range of different physical effects based on real data. So we're using this real data that has been recorded in various locations under various different conditions, weather conditions, and so on and so on. And in addition, we use artificial degradation, which significantly boosts the quality of the deep learning. Like I said, I'm a little bit split on whether deep learning is super great or super nonsense, and I think the boundaries are very small. You can very easily drift in one or the other direction. So, conclusions. For robot to human, oops, sorry, I thought I switched the sound off. Good. Anyway, so for robot to human, lights are easy. They are a good way to use. Sorry, it's muted. Anyway, so lights, they are easy. They have limited expressive power. So when it comes to displays, then some hardware is needed, but you have very high expressiveness. And in my opinion, this hardware is actually not so much overhead. Robot motion I excluded here. I think it's conceptually very interesting, but there are lots of limitations. Unless the gloves are gonna really take off, and I think this could be the case, then gestures perceived with standard underwater sensors like imaging sonars or cameras will be the standard thing. So for the back end, also if you use a smart cloth, Caddy, I think, is the prototypical solution. So quite a lot of thought and energy went into it, and I think it obviously for certain applications can be extended, but it definitely is, so to say, something to easily build upon. For the front end, things are still much more difficult. One important detail, hand segmentation should not be ignored. The gesture classification proper. So there is no perfect solution yet in my view. There is simply this very high variability of environment conditions. Deep learning does have some potential, but it's highly important to not ignore the proper training and also testing. And stereo in general is tremendously beneficial. It eases image restoration, so if you have some depth information about your scene, image enhancement becomes much easier, also segmentation. So some very fast acknowledgements. A lot of the work presented here was also related to the Caddy project, and lots of people contributing to it, especially also from Nicola's group. And if you want to have a look at the references, so there is the PDF, and you can just download it from the web.
Andreas, thank you so much for a really interesting presentation, and also for finishing on time, even though we got started a little bit late. But I think we can have one question.
Another thing working divers use sometimes, not only diver to diver, but also diver to surface, is line pull signals. Has anybody approached that from a robotic sense?
You said light signals. Yes. Yeah, there is at least, I mean, there are one or two papers that mention it. But up to my knowledge, nobody actually used it. And I think one of the deals is also the relatively limited expressive power. Plus, if you use it as a kind of Morse code, I think it's relatively easy, but from all I know, divers also use it a lot to point somewhere, or, to have some kind of signaling which requires quite a lot of cognitive capabilities to interpret what this other diver actually wants to show me, So using kind of flashing lights, kind of Morse code style, I think would be very easy to process from a computer vision kind of viewpoint. Has been mentioned a few times, but I didn't find anything where somebody actually used it.
Are we ready to go here? Are you all ready? Okay. I did see a few more questions, but perhaps you can catch Andreas later, just so we can allow all the speakers their full time. So thank you very much.